Now we're thinking about something a little bit different, electric forces. They are forces, so it's not entirely a different subject. We're still going to be thinking about Newton's laws, among other things. But like any other force, the electric force has a magnitude and a direction. The direction is relatively straightforward. Just remember the old slogan, opposites attract and likes repel. So if you have two charged particles of the same type, there are two different types of charge, positive and negative. We get those names from Benjamin Franklin. And if the two charges are the same type, they are like charges. Likes repel. So the force from one repelling two goes this way, force from one on two, and then the force from two repelling one, the force from two on one goes the opposite way. And then the other half of the slogan, opposites attract. If the two are opposite types of charge, then they will pull each other closer. One or two feels an attracting force from one. There's the force from one on two, pulling two towards one. And then two is applying an attracting force to one. Two is attracting one towards two. That's all there is for direction. Opposites attract, likes repel. Now the magnitude. We have a rule called Coulomb's law, which tells us the magnitude of any electric force between two charged particles. And one factor is K, just a constant factor that you can look up. It's there towards the beginning of chapter 20 if you need to do any calculations. And then since we're interested in only the magnitude of the force, we're not interested in the signs of the charges, because the signs of the charges tell us what the direction of the force will be. So we have just absolute values of the charges, and the force from one charge on a second charge is just the product of the two absolute values of the charges. We're just interested in the amount of charge, the size of charge, the magnitude of charge. We're not interested in the sign here when we're thinking about magnitude. And notice in this slot goes the source of the force, and in this slot goes the other charge, the thing that is receiving the force. So the force from one on two looks like this, K charge 1, charge 2. And then divided by square of the distance between the two charged objects. Flip that around. Instead of thinking about the force from 1 on 2, think about the other force from 2 on 1. So in this force, 2 is the source, so charge 2 goes in that slot. 1 is the thing receiving the force, so charge 1 goes in that slot. Compare these two equations, they give you the same number, because Q1 times Q2 is just the same as Q2 times Q1. That's an important conclusion. Amazingly, surprisingly easy to forget, so try not to forget it. When there's an interaction between two charged things, call them thing 1 and thing 2, the magnitude of the force from thing 1 on thing 2 is equal to the magnitude of the force from thing 2 on thing 1. And that equality is just built into the equation here, because you've got all the same factors in pretty much the same places, whether you're talking about the force from 1 on 2 or the force from 2 on 1. This is true because these two forces are a Newton's third law pair. Right? They are always going to be the same type of force. If you have like charges, the two forces will be repelling forces and pointing in opposite directions, just like the forces in a third law pair. Or if they are opposite types of charge, they'll both be electrical attracting charges, again, pointing in opposite directions, just like the two forces in a third law pair should. Same type of force, always pointing in opposite directions, and furthermore, when you look at one force and then compare it with the other, the roles of source and receiver are flipped around. The thing that is the source of one force is the receiver of the second force. The thing that receives one force is the source of the second force. Or if we talk about actions and then reactions, one acts on two, and then two reacts back on one. That's the pattern for a third law pair. And it's important to note, when I came up with this conclusion, I just compared these two equations and I made absolutely no assumptions about the values of Q1 and Q2. In other words, this is true regardless of the values of Q1 and Q2. These two forces are of equal magnitude, even if Q1 and Q2 are really, really different. For example, let's say there's a charged object with 100 units of charge, and then here's another charged object with only 1/100th the amount of charge. They're like charges, so they repel. This has 100 times more charge than this charge, but the repelling force that this one feels and the repelling force that this one feels are equal in strength because those two forces are a third law pair. So there's force from the 100 times larger charge on the smaller charge, and then there's the force, draw it with an arrow of the same length because that the force this feels is just as strong as the force that this one applies to this charge. This has 100 times more charge. So if you imagine, say, starting with just one Q worth of charge and then adding 99 to make the total charge here 100 times larger, that of course makes the force that this one applies to single Q 100 times larger, but it also makes this charge 100 times more sensitive to forces that come from other places. So you make the charge here 100 times larger, you not only make the forces that it causes 100 times larger, you make the force that it feels 100 times larger as well. This force and this force are equally strong because they are a third law pair. Okay, let's just go back, think about Coulomb's law a little bit. If we leave the two amounts of charge alone and just move those two charged objects around a little, same charges but move them, then everything up here in the numerator stays the same. Everything up in the numerator is constant. So then what does Coulomb's law look like? Force from thing 1 on thing 2 is just constant factors divided by distance squared. And that equation is now in the form of inverse proportionality. One variable equals constant stuff times some other variable, and then the one variable that we call y here just corresponds to the magnitude of the force. The constant factors correspond to k times magnitude of Q1 times magnitude of Q2, and then everything else on this side of the equation that isn't one of those constant factors will correspond to the variable. And in Coulomb's law, everything that isn't one of the constant factors, everything that isn't one of these, is this, d squared, not d, d squared. So magnitude of the force is inversely proportional to d squared. Remember the slogan, the principle of inverse proportionality. When one variable changes by some factor, the variable that it's inversely proportional to changes by the inverse of that factor. So, for example, let's say you've got two charges, Q1 and Q2, and let's say they're both negative charges, so they repel each other. And whatever Q1 and Q2 are, the force that this one feels is equal to the force that this one feels because they're a third law pair. And that force turns out to be, let's say, have a magnitude of 10 to the minus 6 newtons. Magnitude of that force is 10 to the minus 6 newtons. Now, imagine those two charges, since they are repelling each other, they're moving farther and farther apart. And of course, the strength of the electric force depends on how far apart they are. So as they move farther and farther apart, the magnitude of that force changes. How does it change when they become, say, 50% farther apart than they were before? That is, initially, they were just some distance, d1 meters apart. But now, we look at the situation a second time and find that the distance between them is 1.5 times the original distance. The new distance that separates them is 50% bigger than the original distance that separated them. How has the force changed? This was the force originally. What's the new force? Well, remember, magnitude of the force is inversely proportional to distance squared. So we need to figure out how distance squared changes. And of course, we can get that from this just by squaring the whole equation. Square of this equals square of this times square of this, or the new distance squared equals 1.5 squared, which is 2.25, times the old distance squared. So this variable called distance squared changes by a factor of 2.25. Distance squared is inversely proportional to the magnitude of the force. So since the magnitude of force is inversely proportional to this, it will change by the inverse of this factor. It'll change by a factor of 1 over 2.25. Magnitude of the new force is magnitude of the old force divided by 2.25, and that'll come out to 4.4 times 10 to the minus 7 newtons. Now let's look at that same proportionality relationship from a different perspective. Instead of seeing what happens when the distance changes, let's think about how the distance had to change in order to get a particular change in force. That is, let's say initially, two charged particles are 1 centimeter apart, and as a result, they will feel an electric force with a magnitude that we'll call F1, or absolute value or magnitude of F1. Now, we bring them closer, and of course, when we bring them closer, the magnitude of the force gets stronger. We bring them close enough so that the magnitude of the force in the second case, the new magnitude of the force is 3 times what it had been. Okay. So what is that new distance that made the force 3 times stronger? Well, go back to that proportionality again. Force and distance squared are inversely proportional, which means that when force changes by some factor, a factor of 3 in this case, distance squared changes by the inverse factor. So, in other words, the new distance squared is 1/3 the inverse of this times the old distance squared. And of course, what we want to find is the new distance, not the new distance squared. We want to find just plain d2 to the first power, but we can get that easily just by taking the square root of the whole equation. So when we do that, we have plain old d2, square root of this, equals square root of this, which is 1 over square root 3, times square root of this, which is just d1, which was 1 centimeter. So when we ask the calculator what 1 over square root of 3 is, and then multiply it by 1 centimeter, what we'll come up with is 0.58 centimeters. By cutting the distance by 42%, you have tripled the strength of the force. Now, the more interesting situations are a little bit more complicated than this. The more interesting situations are when there are more than just 2 charges interacting with each other. So let's look at an example of that. You'll practice it a lot more in class. Let's see, 3 charges, positive 1, negative 1, and another negative 1. I'll call them A, B, and C. And from now on, the symbolism works like this. 1 sign indicates 1 unit of charge. So this has 1 unit of positive charge, this has 1 unit of negative charge, this has 1 unit of negative charge. In other words, the magnitude of charge on this is the same as the magnitude of charge on this and same as the magnitude of charge on this. The only differences are that the signs of the charge are different. And let's say we want to find the net force on one of those three charges. For example, the net force on charge A is a sum of two forces. A will feel a force from B, and it'll feel a force from C. So net force on A is the sum of the force from B on A, plus the force from C on A. And we don't have any numbers in this case, but we can still get an idea of what that net force is like. We can still say something meaningful about that net force by doing the following. We're keeping things simple here, so the spacing between charges is the same. That is, this distance is the same as this distance, so charge C is twice as far away from A as charge B is. And we'll say that any time one unit of charge feels a force from one unit of charge one step away, we'll say that the magnitude of that force is plain old F. That'll make it easy to think algebraically about these kinds of forces. One unit of charge feels force from one unit of charge. Might be the same sign as this, might be a different sign. Doesn't matter because we're thinking only about magnitudes. Remember, the sign of charge tells us about the direction of the force, has nothing to do with the magnitude of a force. When one unit of charge feels force from one other unit of charge one step away, that's a force that we will call just plain F. For example, in this case, the force from B on A, when we're thinking about the force from B on A, we're thinking about a force felt by one unit of charge coming from one unit of charge one step away. So the magnitude of the force from B on A is what we're going to call just plain old F. And that's the magnitude. What about the direction? Well, A and B are opposite, so A is attracted to B. B is also attracted to A, but we're not interested in that. We're just looking at the net force on A. And A is attracted to B. That is, A is pulled towards B. A feels a rightward force pulling it towards B. And we'll just, as we usually do, say right is the positive and left is the negative direction. So that's a positive force of magnitude F newtons. Now, what about the force from C on A? Let's deal with the direction first. C and A are oppositely charged, so opposites attract. A is attracted towards C. A is pulled towards C. The force on A is pulling it towards C. The force on A is pulling A in the rightward direction, so that's another positive force. But it's going to be smaller than the force from B because C is twice as far away. We can actually figure out precisely how much smaller. Let's go back to Coulomb's law. So force from force from B on A, magnitude, is just K times the magnitude of the charge from B, the source, times magnitude of charge on A, the receiver of that force, times the square of the distance between A and B. Now, write out Coulomb's law in the similar style, but now we're thinking about the force from C on A. Force from C on A is the same K constant times the magnitude of the charge from the source C times magnitude of the charge on the receiver A times square of the distance. Well, the distance between C and A is not D, it's 2D. So 2D is the distance, and we square it. So next thing to remember is that all charges A, B, and C have the same magnitude of charge. So the magnitude of charge on B is the same as the magnitude of charge on C. So in both of these equations, the numerator is the same. The only difference is that the denominator in this force is 4 times larger than the denominator here. This denominator is 4 times larger than this denominator. Everything else is the same about these two forces, so this force is only 1/4 as strong as this force. This force, we said, had a magnitude of F newtons. This is 1/4 as strong, so it would have a magnitude of 1/4 F newtons. And so the net force on A is just F plus F over 4, a grand total of 5/4 newtons. 5/4 F newtons. In other words, the net force on A is just a little bit stronger than the force from B on A. And it points in the same direction as the force from B on A. Now let's try one more. Let's think about the net force on C. That'll come out a little bit different. Net force on C is again the sum of two forces. There's a force from A on C, and there's a force from B on C. Force from B on C is 1 unit of charge applying a force to 1 unit of charge, and they're 1 step away. So that amount of force from B on C we will call plain old F, F newtons. And both B and C are the same type of charge, so they're applying repelling forces to each other. B pushes C away from B. B pushes C to the right. C feels a rightward, in other words positive, push from B. Now, what about the force from A on C? First of all, they're opposite signs, so A and C attract each other. C feels an attracting force from A. C feels pulled to the left by A. In other words, C feels a pulling force in the negative direction from A. And what's the magnitude of that force from A on C? Well, remember this kind of thing. Notice what happened. Comparing this force to this force, The only thing that was different between this force and this force was that the distance got 2 times larger. Well, the distance got 2 times larger, and as a result, the force was only 1/4 as strong. Double the distance, you cut the force down to 1/4. That's just a consequence of the inverse proportionality between strength of the force and distance squared. Double the distance, then the force is now 1/4 what it had been. So since this is twice as far away from C as this one, the magnitude of this force on C will be 1/4 as strong as the magnitude of the force from this one. So if the magnitude of the force from B is plain old F newtons, the magnitude of the force from A is F/4 newtons. And so the net force then is minus F/4 plus F, or 3/4 F newtons. In other words, the net force on C is a rightward force, positive, but it's weaker, but it's 25% weaker than the force C feels from B alone. Most of the other things we do with when thinking about electric force, and for that matter electric fields, are just variations on these same ideas, but it does take a little bit of getting used to, so in class we'll try to get used to some of that.